Alright, welcome back. We're going to continue with our rotation and torque and kinematic stuff. So I'm going through some older free response questions today. We're working
Mm-hmm.
on FRQs from 1999. There
Mm-hmm.
are 3 each year for mechanics. So I'm going to be doing the first one, and then I'm going to leave the other 2 for you for homework.
Mm-hmm.
Our objective is kind of the same as last time, so we're combining principles of kinematics and energy to predict motion.
Mm-hmm.
We've got all of our same formulas that we'll be taking a look at this time around. I'm still dealing with rotation. Okay, so our setup. We've got this lab experiment where we're going to fire a dart at a block that's at the end of a string. We're firing very close to the wooden block, hanging from a chord of length L of negligible mass. Assuming that the size of the block is negligible compared to the length, and the dart is moving horizontally when it hits the left side of the block and becomes embedded in it. The block swings up to a maximum angle theta from the vertical. I want to express my answers in terms of the mass of the dart, the mass of the block, the length of the string, the angle that the string forms when it's at a maximum point away from the center, and gravity to determine the initial velocity of the dart before it strikes the block. So what do I have to do?
So this is we use conservation of oh no, this is just conservation of energy.
Okay, I'm going to start with energy then.
So the um the V initial is the speed of dart. So MV initial is equal to small m plus big M
Okay, you said
plus
mv initial equals again?
big M plus small m.
Okay, I think you're doing momentum, not energy first, but we can do that.
Oh, yeah, it should be energy.
Um, we'll need both, but you can start with momentum if you want. So you said mv initial is equal to what?
M G MGL cosine theta.
Okay, that's energy. So let's finish off momentum and then we'll get back to
Oh,
energy.
plus big M.
Okay,
Final velocity.
final velocity. Okay, then we're going to go energy. Okay, and you mentioned our potential energy, I think I heard. So that was the total mass uh,
Mm-hmm.
times g, and I'm going to write h for now, and we'll substitute. I think you started the substitution,
Mm-hmm.
um, but I'm not sure. I'm going to mark that. So you mentioned something about a cosine, right?
Yeah.
Okay, what did you say?
Oh, L minus L cosine.
Okay, L minus L cosine, you're right. So from here to here is L cosine theta. So L minus L cosine theta would give me the height. Okay, you got the hard part? So this is my mass total is the sum of both masses. Times G times, I'm gonna write it this way, times G times L times 1
Mm-hmm.
minus cosine theta. Okay, should be equal to what?
M 1/2 M B initial square.
Perfect, and that's just the mass. Um, well, hold on. This needs to be the total kinetic energy that we had the moment that they both hit. So that means I need to change this side a little bit.
Mm,
So the moment that the dart hits the block, what would the total kinetic energy be?
1/2. Is it big M? No, is it total M then?
Right. See, if we use the kinetic energy of the dart when it was fired, it's going to lose some of that energy before it actually hits the block, right? So my conservation of energy needs to start the moment that the dart becomes embedded in the block, because that's the energy that will be conserved between both objects. Our energy, we would have lost some energy when the dart was heading to the block first, right?
Mm-hmm.
Okay, so this should be my total M. Total. And then which V is this then?
Pre-initial.
Okay, right now V initial is our dart.
Oh,
So it would
I see.
be at the moment we fired the dart. So this should be big V.
Mm-hmm.
The moment where the dart became embedded in the block.
Mm-hmm.
Okay, I'm going to rewrite all of this. This is 1/2. Our total mass is M plus MO. Big V squared. Okay. So I've got an equation down here for energy. But we actually don't have a V initial in that equation.
Mm-hmm.
So what do I have to do?
So plug in terms of V.
Okay. So I'm going to use our momentum equation to solve for V. And then we'll substitute, so we'll have a VO here.
Mm-hmm.
Okay. So I could say our big V is equal to MVO over M plus MO.
Mm-hmm.
And then resub. Okay, I'm going to simplify this a little bit. So let's simplify one step just so I've got room to write. I'm going to divide both sides by M plus MO, which will cancel these
Mm-hmm.
two.
Yep.
So 1, 2. And then multiply by 2 to
Mm-hmm.
get V squared is equal to 2GL times 1 minus cosine theta. And then we'll plug this in. MVO over M plus MO squared is equal to 2GL times 1 minus cosine theta.
Mm-hmm.
Okay, what do I do next?
And then we're finding pre-initial.
Right.
So we simplified this, but it looks complicated.
What do you think my first step would be to simplify?
Mm, we square root both sides.
Perfect. Okay, oh, that too long. So you're right, we're going to take the square root of both sides. So root 2GL times 1 minus cosine theta
Mm-hmm.
is equal to MV initial over M plus MO. Okay, if I want to solve for V initial, what's going to happen?
And then we times the bottom part.
Okay, so I'm going to multiply by the reciprocal here. So this is M plus MO over M root 2GL times 1 minus cosine theta. Awesome. Any questions on what we did?
No.
Okay, so let's check really quick. Okay, 1 point for using conservation of momentum at any point. We did that. 1 point for conservation of mechanical energy. Okay, we did that too. And starting with the total mass. Okay, calculating H in terms of L, you did that. Substituting M total into the V energy equation. Okay, we actually did the opposite of that, but that's okay. So, and then getting the correct answer. So I'm pretty sure we did the opposite of that. No, never mind, we did do that, exactly. Okay. So that's 5 points so far.
Yay.
Okay, for part B, we're told that our dart and block are swinging as a pendulum. I want to determine the tension in the cord when it returns to the lowest point of the swing. What do I have to do?
So the lowest point.
Mm-hmm.
There is weight and tension.
Okay.
So tension minus weight is equal to MA.
Okay. I could say... Okay, right, tension minus the force of gravity. Should be equal to MA. What is that mass?
Just big M.
Just
Big and small M.
big and
Dart
small m. Okay, both of them. Plus MO. Times A. Okay, and then what is that A?
Acceleration.
What type of acceleration?
Oh, centripetal.
Okay, that's also centripetal acceleration. What's the formula for centripetal acceleration?
Centripetal. That's V squared over R.
V squared over R. What is R in this case?
L.
V squared over L. Okay. Since I have to write this in terms of M naught, L, theta, and G, I'm going to write L instead of R for this case. Okay, and then we'll solve for... We're solving for tension. So we can start to substitute, I think. I think we're okay. Let's see, I'm not allowed to write this in terms of V, though. So I think I'm going to go back to our... the equation we just found for V. So this is from the previous slide. But our equation for V was... here. M plus M over M. Times roots 2GL 1 minus cosine theta, I think. Double check. Yeah. Okay, so I'm just copying from part A. Okay, so now that we've got that, so that gives me in terms of our masses G, L, and theta. Okay, so if I substitute that in, then I should be good to just solve for tension. Okay, so let's go ahead and we'll plug that in. Okay, I'm going to do one step first to solve for tension on this side. So tension is equal to M plus M naught times G minus V squared over L. So I added this term over and then factored out m plus m naught just so I would have space.
Mm-hmm.
Okay, cool. So now we can plug in. I'm gonna go down here just so I have more space to write horizontally. So my tension is equal to what?
Isn't it opposite v squared over L minus G?
Uh,
No, plus, actually add
yeah,
it.
this should be plus. Okay,
Yeah.
sorry, go
So,
ahead.
um, oh, you plug in V in there and then square it, but,
Okay, so m
uh,
plus m naught times g plus. Okay, if I square v, the square root's gonna go away. What's gonna happen to this part?
that's squared.
Okay, so this is m plus m naught squared over m squared l times
Just 2GL inside part.
2gl times 1 minus cosine theta. Okay, can anything cancel?
Uh, Nothing cancels out. No L,
Okay, l can cancel.
that's it.
L can cancel. Um, hmm. Yeah, I'm not really seeing much here either.
So that's the answer. Yeah, we found tension.
Okay. Let's see, I could factor out a g from this if I wanted to. I don't really see much else that we can do though.
Is that answer then?
Okay, well, let's see. So, okay, Newton's second law, we got that. Tension minus weight is our net force, okay. Centripetal acceleration, that's good. Correctly substituting m total and v. M total, okay, we did that. And substituting for v. Um, V squared. In terms of initial, let me go back. So maximum angle, that shouldn't change. Okay, I'm not seeing what we did wrong for our substitution.
Hmm?
I don't see what we did wrong for our substitution.
It's just simplification, right?
Maybe, I still don't see it though. Okay, let's try to
Eh,
simplify further. We'll see what we get. I don't think I can pull anything else out here. I can pull one G out maybe. So this would be G and 1.
uh-huh.
Okay, so that leaves me with M plus MO times G times... Okay... 1 plus 2 plus MOM squared minus 2 cosine theta.
Yep.
So according to this is supposed to simplify into 3 minus 2 cosine theta.
Mm-hmm.
I'm not seeing it. Do you?
No.
Me neither. C minus m plus mg. Okay, we have that. C minus m plus mg, we got that. M plus m times v squared over L. V squared over L, we substituted for v. And divided by L, that's fine. Okay, I do think we would get full credit for that because we did correctly substitute MT and V.
Mm-hmm.
So they didn't give the point for the final solution here, but I don't know how they got from here to here.
So maybe answer is wrong.
No, I think the answer's fine. And I think our answer's fine too. I do think we'd get the
Mm-hmm.
full credit for that point because we did do the substitution that they gave the point for.
Yeah,
I
yeah,
just don't know how they simplified.
yeah. Mm-hmm.
Okay, I'll take another look at it later. Okay. So if we set up a lab table where you had a meter stick, protractor spring, stopwatch, 5 meters of string, a set of known masses, and then 5 more blocks of mass m naught, how could you create another way to determine the velocity of the object? So I want speed of the dart just after it leaves the gun.
Oh. So mm, speed of the dart.
Yep.
Speed of the dart just after leaves the gun. Use conservation of momentum, maybe? Energy?
Conservation of momentum and energy for this system is what we did originally.
Mm-hmm.
So we have to do something different. Because we have to design another practical method. So you can still use momentum and energy equations if you want, but we need a different setup, so it can't be this setup.
So maybe we use kinematics this time then.
You can use kinematics, you can use energy, you can use whatever you want, but we can't use this setup. So what I mean is, your picture needs to change. How are you going to set your experiment up using these objects instead? In order to figure out what the velocity of the dart is when it leaves the gun.
It's hard to think about other experiment.
So you can create almost anything you want, as long as you can find a way to measure it. So forget about this picture completely. All we have is our dart gun, and the dart so far. Okay, what else do you want?
I don't know.
Can you take a guess?
Maybe stopwatch?
Okay, how are you going to use a stopwatch?
Time displacement divided by time to get velocity.
I think that's going to be really hard to measure if you're just looking at the dart itself. You're also going to get an average that way. And I want the instantaneous velocity that it leaves the pistol. Maybe you can shoot it into something? We were given a spring. And some string. So how could we use the spring?
Oh, kx is equal to mv, no mg.
Okay. So I think what I'm going to do is I'm going to set our mass to hang off the spring instead. Spring, mass. I'm going to shoot the dart straight up with the pistol. Into the spring. Okay. And then we'll use that to try and figure out what the muzzle velocity is. Okay, so step one, before we actually shoot the block, what do I need to know first with just the spring and the mass?
K.
K. Okay, how can I find K?
So we hang the, and then we measure the horizontal displacement with ruler, meter stick.
Okay, so we're going to use the meter stick and we're going to measure the vertical displacement in this case.
Vertical displacement.
Okay, so I'm going to, hold on, so we're going to hang
Of course, and
mass on spring. I'm going to hang spring to ceiling. And measure equilibrium. Then step two, hang mass to spring. And measure displacement, you told me?
Yep.
Okay, if I know displacement, then how can I figure out what K is?
Oh, kx equals mg.
Yep. Kx equals mg, therefore k is mg over x. Okay, now I know the spring constant.
Mm-hmm.
Okay, step 4. Okay, now I'm ready to bring in the pistol. What do I want to do with the pistol?
We shoot it vertically.
Okay, and then what are you going to measure?
The displacement.
Okay, measure displacement. With meter stick. I should have mentioned that for all of these. With meter stick. Okay, measure displacement with the meter stick. So we're going to see how far the spring is compressed.
Mm-hmm.
Okay, what do we do after that?
Then we use the other equation.
So which equations are you using?
Oh wait, so shoot it vertically.
Okay. What happened to our energy once you shot it vertically and you measured the displacement?
Oh, it's mga is equal to 1/2 mv squared.
Okay, cool. So we can calculate spring potential energy.
Mm-hmm.
US. Okay. Once we know the spring potential energy, then we should be able to solve for the initial kinetic energy. That?
Yes.
6. Solve
Oh, I got it.
for
Knew it. How to do it.
initial kinetic energy. Okay, just as a general outline. I'm sure there's more than one way to do that. And if I go over, you can see they don't actually give us a procedure for the key. And they're just looking for some sort of practical procedure where all of this can be done. So, okay. So 4 points. Practical procedure that used some of the apparatus. Recognition of any assumptions that have to be made. Okay, I don't think I made any assumptions here.
Oh,
Um,
assumption?
Yep. What do we have to assume for this to work?
No air resistance.
Okay.
Yeah, no air resistance.
Sure. Indication of proper mathematical computation using the variables measured. Okay. We mentioned how we could get there.
Mm-hmm.
So I'm gonna say we would have got 3 out of 4 because we didn't make any assumptions that we didn't make any list of limitations or anything.
Mm-hmm.
Okay. And last one. So our dart is shot into the block of wood, but this time it's fixed in place. The block is exerting a force on the dart that is proportional to the velocity in the opposite direction. Force is negative BV, where B is some constant we don't know. I want to derive an expression for the distance that the dart penetrates into the block. Okay, so now, again, my picture doesn't count. Instead, we've got our dart, which is going into a stationary block,
Mm-hmm.
and the block is not moving after it comes in. So I want to know how far into the block it will penetrate. Okay, so they gave us F equals negative BV to start out with. What else can I do here? What is my force equal to?
Force equal to MA.
Okay, MA is equal to negative BV. Okay, so I need this in terms of M, V initial, and B, which means I can't have an A in this equation. So how can I rewrite A?
Oh, so A is D square X divided by D times square.
You're saying second derivative of displacement, I think.
Yeah.
Okay, to get there I'm going to need to do a first derivative first though. So A right now is equal to what?
D dv over dt.
dV over dt. Okay, it's important because I've got more than one variable here. So I can't just integrate twice on this side because I don't have the same variables.
Mm-hmm.
So because I have a separable differential equation, I've got v's on this side. I need to separate my variables before I can integrate. So what's my first step?
So we write in terms of dt divided by dv, and then we derive it.
We need to integrate. We need to integrate twice in order to get to displacement, right?
Yeah.
So my first step needs to be to separate my variables. So how can I separate my variables?
One side is dv over v, and the other side is the left part, which is minus b or minus b dt divided by m.
Okay, now this is just a constant. So when I integrate, I'm going to get that times t.
Mm-hmm.
Okay, but when I integrate this side, so we need to integrate
That's ln.
both of these. Okay. So when I integrate the other side, this will be right natural log of v.
Then e to the power minus v t
Okay,
divided by
well,
m.
hold on a minute, because we actually have bounds for this. So I'm going to go back a step. What are my bounds for the left side? Integrating from what to what?
Oh, 0 to b fine. 0 to v.
We didn't start with zero velocity.
0 to
If we didn't start with zero, what should our initial be?
we found it in A, isn't it?
Different equation. So d is its own problem. So
0 to infinity?
nope. So when we first fire the dart, I would have velocity initial. Okay, then when we finish, we'll end up with some velocity.
Mm-hmm.
So I'm going to go from starting velocity to ending velocity. My time is going to start at 0 and go to time. Okay, so when I integrate, I would get natural log v from initial to final is equal to negative bt over m from 0 to t. Okay, plug in for upper bound minus lower bound.
Mm-hmm.
What do I get on this side?
ln v divided by m initial.
ln ln v divided by v initial.
Mm-hmm.
Okay, and then this is negative bt over m. So this is bt minus 0. Okay, and we're good. Now, before we can integrate again, I'm going to move some things over. If I want to get this side just v, how can I rewrite this? So solve for v.
Oh, e to the, so that's e to the minus bt divided by m is equal to v divided by v initial, so times v initial.
Okay. Now v initial is a constant, so I can leave that there. Negative b over m is a constant, I can leave that there, which means I can integrate both sides again. I'm going to integrate the left side in terms of v. I'm going to integrate the right side in terms of t. Now the reason why I did that is because this is a natural log. So I would have had to use integration by parts if you didn't rewrite this first. So this is quite a bit easier, right?
Mm-hmm.
Okay. If I integrate v in terms of v, what happens?
That's you get vt, no x. No, actually,
Okay, I'm gonna make a substitution. Actually, how can I rewrite v?
v is dx over dt.
Okay, dx over dt equals vo e to the negative bt over m. I think that makes more sense. Okay, then solve here. Okay, now what?
Then, oh yeah, we integrate this, so it's
Okay, bounds are important. I'm going to integrate my displacement from what to what?
from 0 to some point.
Okay, I'm going to call that L. So that'll be our maximum displacement inside the block. Is equal to, on this side when I integrate, what are my bounds?
Zero to some point. Infinity?
0 to, what am I integrating in terms of?
Huh?
What are we integrating in terms of on the right side?
T.
Time. So do I want time to go up forever?
No, just sometime.
Just some time. Okay. All right. So on this side, I'll have, if I integrate in terms of x, I just get x, and then I can plug in L minus my 0. Gives me what we want, the displacement, is equal to, on this side, when I integrate, what's going to happen?
That's just T from there. Times T.
Okay, it's not a constant. That's e raised to the negative bt over m. So I do have a variable in that exponent. So what's going to happen when I integrate?
Oh, so like we write the same and then times minus b over m.
Close. That's what would happen if I would derive. But if I
Oh,
integrate,
minus m over v,
there we
m
go.
over b.
Yeah. Okay, so this is minus m over b, v initial, e to the negative bt over m from 0 to t. Okay, then I can plug in t and subtract what happens when I plug in 0. When I plug in 0, what's going to happen?
Um, that's 1. No, only minus mv
Right.
initial divided by.
Okay, so this will be this thing that I have right now, plus
Mm-hmm.
mvo over b. So that could be mvo over b, since I've got that in both terms, times 1 minus e to the negative bt over m. So I've kind of changed the order here because my plus 1 was on the right side, and then my left side would be negative, but it means the same thing. Okay, rewrite my
Mm-hmm.
final answer on this side. L is equal to mvo over b times 1 minus e to the negative bt over m. Okay, any questions on what we did?
No, it's hard though, this one.
Okay. So let's check. Expressing acceleration as the derivative, 1 point, okay. And then general expression for the length of the dart as a function of time. Okay, that's our formula that we did. So we're okay. Okay.
Mm-hmm.
So we've got the last two problems that are up on Skype, and that'll be
Mm-hmm.
it for today. Any questions on anything?
No.
Okay.
Wait. So when do you go back to school?
Okay, so they will give us 3 weeks notice, but we don't know yet.
So it will be 3 weeks later, at least 3 weeks later
Then when
than March 2nd, right?
it'll be 3 weeks later than whenever they announce it. So if Miss Martinez announces it tomorrow, then we start school in 3 weeks. We're waiting on the Ministry of Education to tell us when we can legally start. If they tell us we can legally start 2 weeks from now, then we'll start 3 weeks from now. Miss Martinez will give us 3 weeks. The reason why is because everyone coming back into Shanghai, if you're in another country, has to go through 2 weeks of quarantine.
Oh.
So if you were to come back right now, you would have to spend 14 days at home.
Oh.
But that's true for all of the students and all the teachers. So just to make it easier, they're giving us 3 weeks. That gives you 1 week to buy tickets in advance and not pay top price. And then 2 weeks to go through quarantine so you can actually come back to school on time.
Mm-hmm.
So no set date yet.
Mm-hmm.
Alright, so I'll see you tomorrow.
Wait, so homework is in WeChat right now?
I think I sent through Skype, but I'll send again through WeChat.